Okay, many of you ask about midterm. So I was looking at the academic calendar. I think it says November the 10th is a holiday, so I'm thinking maybe midterm. We will arrange midterm in November the 10th, 11th, 12th. It's like today is Wednesday, this one, right? So the next week, the next weekend, I will try to post the midterm exam problems on Canvas by the midnight of 9 and 10, and then you will have 3 days to work on the midterm and then submit by the midnight of Sunday. Okay. If you have any suggestions or any constraints, please let me know. Okay, so hello everyone, welcome to 130B, Quantum Mechanics. Today we are going to continue our discussion of angular momentum. Let me first review what we have learned so far. We have started from angular momentum operator, which is a vector of 3 components. Every component is a Hermitian operator with these commutation relations. We define its J squared and J3, and then we find also J plus minus. And then we find how these operators act on eigenstates. And then we also understand that these eigenstates are labeled by 2 quantum numbers. One is the angular quantum number. The other may be called magnetic quantum number. So one is usually denoted as J, which takes integers or half integers. The other denoted as M, which goes from minus J to J. So the J quantum number is very stable. No matter how you rotate the system, J never changes, but M can change. M can change by raising and lowering operator. So this angular momentum is used to describe how fast or how much momentum is stored in the spinning of a particle. So every particle can carry a spin, and this angular momentum labels the spin of the particle. It can be spin 0, spin 1/2, and so on. So when we talk about spin 0, in classical mechanics, it simply means that the rigid body is not rotating. But in quantum mechanics, it's hard to say whether an object is rotating or not. Because if you want to know absolutely that the particle is not rotating, you need to measure the angle or the orientation to infinite precision in order to make a statement of that. But angle, just like position or coordinate operator, also has its uncertainty relation associated with that. So in quantum mechanics, you actually cannot measure angle precisely because angle and angular momentum, there is another pair of these uncertainty relations that if you measure angle too precise, then the angular momentum will be very imprecise, and then that will cause a lot of rotation energy, which is not affordable, maybe. So in quantum mechanics, the meaning of a spin 0 particle is actually not that, or maybe you should not think of it as a particle not rotating, but as particle looking, if you look from different angles, they look the same, meaning that a particle that preserves rotation symmetry, no matter from which angle you look at the particle, they look the same, then that's spin 0. And then if the particle has a non-zero spin, that means it looks different as you rotate it. And then if it is spin 1, that means it looks different as you rotate. For example, as you rotate it, it looks different. But if you rotate by 360 degrees, then it becomes the same. That is a spin 1 particle. What about a spin 2 particle? You rotate by 180 degrees, it becomes the same. So if it is a spin J particle, if you rotate by 2 pi over J, that looks the same. So that's the meaning of a spin of a particle. But then there comes a very interesting problem, which is the spin 1/2 particle, which means you rotate by 2 pi over J. J is 1/2, so 2 pi over 1/2 is 4 pi. So you need to rotate twice, 2 rounds, and become the same. So that spin 1/2 particle is really very quantum mechanical nature. It has no classical analog because for any classical object, if you rotate along a certain axis by 2 pi angle, it always returns to itself. But there is particles like spins, spin 1/2 particle like electrons, which you rotate by around 360 degrees, it doesn't come back to itself. You need to rotate by twice, 2 rounds. So that basically has to do with the fact that we will see this effect soon. So, okay. So that's what I want to talk about today, about rotation operator continuing what we discussed last time. So these angular momentum operator are also Hermitian operator, and if you combine this angular momentum operator with angles and raise it to the exponent, of course, I need to emphasize this is an operator exponent, not element-wise exponent. So if you matrix exponent this operator, this Hermitian generator generates a unitary transformation. And the unitary transformation will be labeled by the amount of angle that you rotate. And this theta is a vector which not only characterizes the amount of angle, but also characterizes the direction along which the rotation happens. So this theta completely parameterizes a rotation, and the corresponding rotation operator is denoted as this unitary operator. The operator is meant to be act on a state. And the state is a quantum state. For example, if you have a spin 1/2 particle, then it has 2 basis states, up and down, corresponding to j equals 1/2, but m can take 2 different values, plus 1/2 or minus 1/2. So we need to understand how do we need to change the basis if we perform a rotation specified by certain angles, angle vector theta, for example. So for example, we want to rotate along the z-axis. Then the theta vector is simply 0, 0, z, meaning that along the z-axis we rotate by theta, but along x and y-axis we are not going to rotate. In that case, the rotation matrix or this rotation transformation is represented by this unitary matrix, and this matrix tells us how upspin and downspin gets rotated. So this may not be very obvious, but you can consider a scenario. This is the z-axis. For example, this is x and this is y. And previously, we have learned that if you have a spin 1/2 particle along the positive x direction, which means sigma x equals +1, this state is actually represented as 1 over square root 2, right? And then if you have, so that's a spin like this along the x direction. If you consider another spin along the minus x, x equals -1 direction, that is 1 minus 1 over square root 2. The reason that I want to talk about these 2 examples is if you apply this rotation operator by, let's say, theta equals 0, 0, pi, let's say. So I want to do a pi rotation along the z-axis. So this rotation matrix corresponds to rotation along z-axis by angle pi. So from the physical intuition, if you start from a spin which is pointing along the positive x direction, now you rotate it by angle pi along the z-axis, it goes to the negative x direction. And is that the case? Well, you can verify. You can apply this matrix. This matrix, now, this r of theta, suppose theta is pi, it basically corresponds to e to the I pi over 2, e to the minus I pi over 2. But this pi over 2 is essentially just I and minus I, basically. So indeed, up to an overall factor, if you apply this diagonal matrix on this vector goes to I times 1 minus 1 over square root 2. So it doesn't quite look like that, but only up to an overall factor. But previously, we have mentioned that this overall factor, complex factor, doesn't matter. It's still the same state, as long as the relative phase between the 2 components is the same. So this is how basically this rotation is implemented. So although this rotation at the first glance doesn't look at all like any rotation, doesn't have any intuitive physical meaning that it really rotates things along the z-axis. But when you really apply it to any quantum state, you can check it for another eigenstate, which is sigma y equals +1 or -1. You can also change the angle. For example, you don't want to rotate by pi over 2. For example, you can do this exercise and then check. And you will find that indeed, it basically rotates every these state to the other states as we expected by the rotation angle. So, so any state in the xy plane gets rotated to whatever state it should be. Okay, so this really represents how we implement rotation on a spin 1/2 particle. And for the spin 1 particle, well, the spin 1 particle actually is like an object. It's like a arbitrary vector in a 3-dimensional space. So this spin 1 rotation is more intuitive because for spin 1 particle, it really likes the 3 XYZ axes are really also labeled by the by the basis vectors. So in this case, when you perform the rotation, that basically means that the z component. So if you draw a vector, it basically means that, for example, it's an n vector. That basically means nx, ny, nz. Or another way of saying is like nx times x plus ny times y plus nz times z. If you combine these bases with these vector components, and then this rotation operator tells you how to perform basis transformation. So the z component will not change under the rotation, but the xy component will rotate into each other, following this cosine and sine formula. I think just do some linear algebra, it will be clear that it is indeed rotating in the xy plane. Okay? So finally, I want to talk about when theta equals 2 pi case, which is the interesting case. When theta equals 2 pi, then if you substitute 2 pi into this formula, sine 2 pi, and sine 2 pi is basically 0, cosine 2 pi is basically 1. So you recover the identity matrix, which means if you rotate by 2 pi for a spin 1 particle, the particle doesn't change, it goes back to itself. But if you just rotate 2 pi for a spin 1/2 particle, according to the expression up there, if you substitute 2 pi there, and 2 pi will be divided by 2, then that becomes e to the I pi. E to the I pi is actually -1. And then this matrix doesn't become identity, but becomes minus identity, which means that it's very subtle. It's like the state already returned to itself, but it returned to itself with an overall phase factor in the front. And then, although we say that this phase factor doesn't have physical significance, but if you just look at the states, it seems that you need to rotate by 4 pi in order to restore to itself. So this peculiar minus sign, meaning that actually there's a mathematical saying, that's saying that spin 1/2 is a projective representation of SO3, rotation is basically SO3. Actually, it becomes a representation of SU2. SO3 is a 3-dimensional orthogonal matrices with determinant equals 1. All these kind of matrices form a group, and then the group is called SO3. Each such matrix can be used to represent the rotation in 3 dimensions. But then mathematicians found that all these matrices can be somehow projectively embedded in a larger group, which is SU2. U2 is a unitary 2 by 2 matrices with determinant equals 1. So for example, this is a SO3 matrix, this is a SU2 matrix. 2 by 2 unitary, this is 3 by 3 orthogonal. Yeah, the fact that the spin 1/2 particle after 2 pi rotation doesn't come back has actually to do with the fact that it actually carries a string. For example, if I take this, this is an electron. But this electron, if it is not a standalone particle just in the vacuum, but suppose there's a string, like my arm attached to that, then if I rotate by 2 pi, my arm will be twisted. So although this particle comes back, it doesn't, for example, if I rotate by 2 pi, it doesn't fully come back. I think I need to somehow, I can't do that because my arm hurts today, but you can try yourself. If you rotate 2 rounds, this twist can be recovered, and then there's no such a minus sign. So this strongly indicates that electron is not a standalone particle. You cannot define a single electron. And in particle physics, all these spin 1/2 particles correspond to fermions. There's a theorem called the spin statistics theorem, which says that all the bosons carry integer spin, all the fermions carry half integer spin. And the reason that fermions carry half integer spin is because fermions are topological excitation in the sense that fermions can only be created by pairs. And then that's why there's always an invisible string attaching between each pair of fermions. And it is because of that invisible string that gives these fermions such a weird, peculiar spin 1/2 behavior. Okay, those are some that doesn't matter if you don't understand. Okay, so the next part, I'm going to discuss angular momentum or the spin of a particle in a deeper, to a deeper level, which is about, so okay, we already understand that these particles can have different spins, 0, spin 1/2, spin 1. But in our universe, we have many particles. And sometimes we want to ask, if I combine two particles together, for example, if I have a proton and then an electron, and then they can combine together to form a hydrogen atom, for example, then in that case, proton carries spin, electron carries spin. Maybe there's still angular momentum between them. But if they assume that there's no relative angular momentum, then I would like to know what is the overall angular momentum of the whole system of the hydrogen atom. So in those cases, we need to understand how to fuse different spins together, combining different spins together. So in order to understand that, the mathematical foundation to understand that is called the fusion category. Well, category theory is a very important theory in mathematics. Maybe you haven't heard about it, but it already revolutionized the modern mathematics. Maybe you know that mathematics based on principle or theorems or axioms. Previously, people tried to build mathematics on axioms about sets. And in the 50s or 60s, and people realized set is not enough. And then that is where category theory started. And then now all the mathematics is basically based on axioms of categories. Categories is basically something like a set. So in a set, we basically have a collection of objects. But in category theory, we not only have a collection of objects, but we also need to describe the relationship between the objects. So category theory is describing a bunch of mathematical objects and their relations. So of course, that's too abstract, but we will use example to demonstrate that. So maybe let's just look at these examples. So the objects here are these spins. For example, I have two spins and I want to fuse them together. So this describes two objects fused into a single object. So this process basically is a relation, is some kind of relationship between objects. And these relationships are basically using category theory. You can describe them. So for example, if I have a spin 1/2 object, I can name the two spin 1/2 particle as A particle and B particle. And first of all, I want to understand what is the Hilbert space of the system. So for the A particle, because it's spin 1/2, J quantum number is 1/2, M quantum number can take plus or minus 1/2, it has two states. For B particle, you also have two states. So if you combine the two particles together, altogether, the two particle system can have four different spin states. Either both of them are up or up, down, or down, up, down, down. So that's the idea. And because the bases just need to tensor product together, then the same will happen to angular momentum operators. Remember, every operator is a matrix that is going to act on this state or represented in this state. So for example, SA is a matrix. And SA matrix is like, previously we know, SA is like a sigma Pauli matrices, right? Pauli matrices will be a 2 by 2 matrix here. So what does this notation mean? This notation simply means that SA, when it acts on this two-particle system, it only applies the Pauli matrix to the A particle, and it applies the identity matrix to the B particle, meaning that the B particle is not affected by the action of SA, because SA is supposed to be the spin operator of the A particle, not for the B particle. And vice versa, for the B particle, there will be only a 2x2 Pauli matrix acting on B, but on the A particle, it will be a 2x2 identity matrix. So suppose I want to write down this matrix representation. The way to do that is if you forget about how to do tensor product, maybe you need to go back to the previous part of the lecture, part 1, where at the very beginning we describe how to do tensor products, I think. So, for this case, let me remind you again. For example, I want to write SAX, then it will be 1/2. So first of all, Pauli X is like 1, 1, 0, 0. And then tensor product, so this is the Pauli X for A particle. This is for B particle, I want to do identity. So both matrices, when the X on a single spin 1/2 particle is represented as a 2x2 matrix because a single spin 1/2 particle only has 2 states. So there's only a 2x2 matrix acting on them. But for the two of them combined together, there are 4 states. How can I construct a 4x4 matrix out of these 2x2 matrices, right? The way to do that is this, which we call the tensor product. Tensor product is performed in such a way. First, you take the matrix on the right-hand side and make copies of it. So I will make copy of this matrix. So 1, 1, 0, 0, 1, 1. This is just identity matrix, and I'm going to make copies of them. After you're making copy of the second matrix, you expand the first matrix, and then use all these matrix elements as coefficient in front of the second matrix. That means what needs to appear here is 0 multiplying this matrix. What needs to appear here is 1 multiplying this matrix, and so on. So you can see when 0 multiply any matrix, it cancels, basically annihilates all the matrix elements, so the 4 matrix element becomes 0. And then the same thing happens here, that it becomes 0, 0, 0, 0. But 1, when they multiply on any matrix, it remains the same. So the matrix look like 1, 1, 0, 0, and then 1, 1, 0, 0, okay? So this is the matrix representation of applying a spin 1. Okay, there's a spin 1/2. So there's an overall half vector, 1/2 vector in the front. So this is the result. But let's try to make sense of the result. So if I start from, if I don't look at the B particle, just look at the A particle. If I apply the SAX on the A particle, what am I supposed to get? I'm supposed to take the upspin to downspin, and then I'm supposed to take downspin back to upspin with the overall 1/2 factor, right? This is because if you apply this matrix on an up and down kind of state, you will exchange the 2 components of the state, right? So is this still true when I apply it on this 4 particle basis? Let's try to see that. So we can do this up, up, and then up, down, and then down, up, and then down, down. We can also label up, 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 down, down, up, down, down. By saying I'm representing this operator in the 2-particle Hilbert space, I really mean that I represent this operator. I just describe its action on this 4 basis state. So this matrix, notably, it has 4 basically non-zero matrix element here. So this matrix element is taking down up to, for example, up up. So we can write down the rule here. Down up, this state will be taken to up up, maybe with a half factor, which is not very important. And then down down will be taken to up down, also with a 2 overall factor, unfortunately. And then up up after applying this matrix will be taken to down up, and then up down will be taken to down down. So looking at these rules, you can see from down up to up up, the B particle never changes, but A particle really gets flipped from down to up. Here, the B particle is down, so it never gets changes, but A particle gets flipped from down to up. And then B particle is not changing again, but A particle flipped from up to down. B particle is not changing, A particle, I think, A particle flipped from up to down, okay. So that really, these rules work so well that it basically reproduce whatever this sigma A x need to apply on the A particle and not changing the B particle. So if you want to describe something like that, only thing you need to do is to tensor product these two matrices here. Tensor product has such a nice mathematical construction. If you just follow the definition of tensor product, expanding the first matrix, multiplying the copies of the second matrix to form a larger matrices, this larger matrix in the larger Hilbert space will automatically implement the same operation on the A particle without touching the B particle, without changing the B particle. So that's why we need to do tensor product here. And that's why this spin operator has to be written in this way, okay? Any questions? Yeah. There's an exercise. Try to write down matrix representations of all these SA, SB. I think there's answers here. So if you're not familiar with this tensor product, you can go through this exercise and see whether your answer is consistent with the answer there, okay? So, so this is how we define angular momentum operator in the larger Hilbert space, which contains two spins for both the A particle and B particle. But remember, these are not just operators. These are also physical observables. These SA and SB both contain three components, and each component is a 4x4 matrix, basically, as an operator. So, so we really can add them together. So we can define an operator S, which is the total angular momentum, which is SA plus SB, which means that for each component of this SA operator, so SAX plus SBX basically is SX. And then the same thing happens for SY and SZ. So with that, first of all, one can check that if you add the angular momentum operator of two spins together, the total angular momentum as this S operator still qualifies as an angular momentum operator. That's why we still call it angular momentum, because it satisfies the defining relation that S cross S is identity, is I times S. Again, it has this property, and then this corresponds to something maybe people can call it the total angular momentum of the combined system. And they are also generators of the global SU2 symmetry. So if you consider SU2 as a spin rotation symmetry, and then these angular momentum are generator of this spin rotation as we just explained, and then you can define SU2 for the A particle, for the B particle separately, then that's not called a symmetry. That's not a global symmetry. A global symmetry is that when you apply the symmetry transformation, all the particles in the system transform in the same way. For example, you want to rotate along z-axis by pi, then both particles will rotate along z-axis by pi. That's a global symmetry. So that kind of global symmetry can be simply generated by this S operator, okay? Which means you take a theta times S and then raise it to the e to the I theta dot S, raise it to the exponent, and that whatever that 4x4 matrix is, remember each component of this S operator is a 4x4 matrix like that. And then no matter what that 4x4 matrix after matrix exponential is, that's a 4x4 matrix that implements the global SU2 rotation. There's an algebraic relation of S squared. So S squared can be rewritten as SA squared plus SB squared plus 2 times SA dot SB. But because we know that SA squared is like acting on the spin 1/2 particle. Spin 1/2 particles simply have quantum number j equals 1/2. So when j equals 1/2, the angular momentum squared operator basically takes eigenvalue of j times j plus 1. So j times j plus 1, when j equals 1/2, it's basically 3/4. But when we have SA and SB, this is 3/4, this is 3/4. So together, they contribute 3/2 and plus twice of SA dot SB. So in order to understand the property of the S square here, we just need to understand the property of SA dot SB, because, for example, if we can diagonalize SA dot SB, then no matter what eigenvalue we obtain, we just substitute it into this formula, we will understand the eigenvalue that is associated with S square. So what does SA dot SB look like? It looks like that. That's the 4x4 matrix. If you want to verify, previously, I think in the previous exercise, you will be able to calculate what does SAX, SAYZ, what do they look like as a 4x4 matrix. You just need to combine them following these, I think it's like this. You just need to expand them. This is the definition. And then there's a lot of 4x4 matrix. Unfortunately, you have to multiply and sum together. I think if you go through all these tedious process, this is the result. This is what SA dot SB looks like. And this matrix, if you look at it, it's not a trivial diagonal matrix. So, for example, the SA matrix is really trivial. SA matrix really looks like SA square. SA square. This square in this basis is trivial because it looks like 3/4 and then followed by 1, 1, 1, 1. But S square is not trivial because S square is like identity plus SA dot SB. It's because SA dot SB is not trivial. So in order to understand what are the fusion outcomes of these two spin 1/2 particle, the two spin 1/2 particle comes together, and the total angular momentum square will be computed using this matrix. So it is very instructive to diagonalize this matrix first. So we can perform a matrix diagonalization. You can use Mathematica. You can calculate by hand. But the answer is that this matrix has four eigenvalues. One is different from the other three. So there is one single eigenvalue which equals minus 3/4. And then this corresponding to a state where S square equals 0. So if you still remember that, that the relationship between S square and SA dot SB is this. So if SA dot SB takes certain eigenvalue, you can substitute that eigenvalue into this formula and infer S square. Why do we want to infer S square? Because S is the total angular momentum, and S square is the square of the total angular momentum. And the square of the total angular momentum, its eigenvalue basically labels what is the J quantum number associated with the combined spin system. So that's why we want to understand if we fuse two spin 1/2 together, what can we get? We basically need to compute the eigenvalue of total S squared. That eigenvalue will tell us what's the J quantum number or the S. So for general angular momentum theory, we call J, but here I just call it S. S is the, it's like J, it's the spin quantum number, okay? So this total S square is supposed to be, let me write it here. This S square quantum number, this S square eigenvalue is supposed to be S times S plus 1. So by calculating the eigenvalue of this operator and matching this formula, we can figure out what this spin S is. So we first compute this eigenvalue, and it tells us S square equals 0, which infers that this S must be 0 because there's no other solution which can make this hold for any positive S, non-negative S. So this basically means that this eigenstate should be labeled by the total angular momentum S equals 0, and then the so-called MS. There's another magnetic quantum number associated with that. It can also must also be 0 because there's no other choice. This m quantum number can only go from minus j to j. And here j or s equals 0, so this second quantum number can only be 0. And the corresponding state, how does it relate it to the previous 4 basis states? Well, by diagonalizing this SA.SB matrix, I think, sorry, I think you can figure out the eigenstate. I just write it down. The eigenstate is this spin singlet state. So you can see that the spin singlet state has 0 spin automatically emerge by diagonalizing SA.SB. There are other 3 eigenvalues which are degenerate, which correspond to 1/4. And then when SA.SB is 1/4, you can calculate that S squared is 2. When S squared is 2, you can further calculate that this little s is 1 by this relation. And then when the little s is 1, that means the total, the 2-spin system as a whole is in a spin 1 representation. And the spin 1 representation, we know it has 3 states. And nicely, we have 3 states degenerate with this eigenvalue. So those 3 states can be organized in such a way to form the 1 plus 1, 1, 0, and 1 minus 1. These are the state vectors associated with the triplet states. So that's what we can see here. Yeah, so basically this formula tells us if we combine 2 particles of spin 1/2, which are labeled by up and down separately, how do we combine them in such a way that we can obtain a spin 0 state, or we can obtain 3 different basis states which carry spin 1. So that means 2 spin 1/2 particles fused together can either be a spin 0 or be spin 1. There are 2 different fusion channels. So that's what people say that. And then you can also represent all the S operators. So this S operator also has 3 components, Sx, Sy, and Sz. If you represent it as the original spin 1/2 tensor product spin 1/2, which is this basis, in terms of up and down, it looks like this, these 4x4 matrices. But if you try to represent it in a new basis, which is 0 plus 1, 0 plus 1, this, this tensor plus simply means direct sum. Direct sum means that you just arrange the bases together. Direct product is like you product the bases together. For example, this spin 1/2 corresponds to up and down. If you tensor product with up and down, it is spanned into 4 different combinations. But direct sum just means you just put the bases, just concatenate the bases together. For example, 0 corresponds to this state, and 1 corresponds to 3 states because there are 3 states that has spin 1. So 0 plus 1 means that you are going to arrange your bases such that the first basis state is from the 0 sector, and the later 3 basis states are from the 1 sector. And how are these 4 states related to the previous 4 states? Well, the relationship is up there. I have already written down. We have already defined how the spin singlet and spin triplet state are rearranged or rewritten in terms of the original basis. So you just use those relations. You can transform these matrices into the new basis because you just need to rewrite the basis state. And then you can see that in this case, I couldn't show all of them together, but in the original basis, S1, S2, S3, they are not fully diagonal. But in the new basis, it's very nice. That's why we want to do this exercise. It's nice in the sense that you can see every matrix splits into 2 blocks. And the 2 blocks is labeled by a 1x1 block, which is correspond to this 0, 0 state. And then a 3x3 blocks, which correspond to the spin 1 sector. So this simply means that if you combine 2 spin 1/2 particles together, in terms of the operator representation, all its angular momentum operator will originally take a very complicated form. But if you are able to do some nice basis transformation, look at the problem from a different angle, from a different basis, problem will be simplified. You will figure out that this complexity is not necessary. This complexity can be fully ascribed into the 2 different blocks if I recombine these states into a new set of bases, such that on the new set of bases, the way that S1, S2, and S3 acts on the basis state exactly is the same as the way we expect it to be on these spin basis. Because we previously know if we apply an angular momentum operator on a state labeled by J and M, where it should go, right? How it should look like. So it will reduce to those previous familiar problems. So instead of trying to figure out the action of this operator in such a complicated form, you can directly use the previous matrix representation of all these spin or angular momentum operator that we have already learned in the previous section, and then just just concatenate this matrix and that matrix together. It will become it becomes another representation of these operators. And very notably, this S-square operator, if you represent in the spin 1/2 tensor spin 1/2 basis, it's not diagonal, non-trivial. But if you try to diagonalize that, it will become a diagonal matrix. And this 0 basically means that this is a spin 0 sector. This 2 means it's a spin 1 sector. 2 means this eigenvalue is 2, and this little s is spin 1, okay? So this is really the meaning of what we mean by spin 1/2 and spin 1/2 fused together can become spin 0 or spin 1. The original basis is from a so-called reducible representation. And the new basis, either this basis or that basis, separately forms irreducible representation, meaning that if you multiply or if you fuse two spin 1/2 representation together, the basis becomes a 4-dimensional basis, but that basis is too large. This 4-dimensional basis can be recombined, reorganized, and then split into two irreducible representations. One is spin 0, the other is spin 1 of SU2 group, okay? And these two bases are really related by so-called basis transformation or basis projection. So if you just tensor product spin 1/2 particles together, it seems that your Hilbert space contains 4 states. But if you are allowed to do a projection operator, these formula are just rewriting of the previous formula, but in terms of matrix form. So if you project these 4 states using this matrix, then this matrix automatically combines these states together into the singlet state. For example, this matrix simply means 0 multiply up, up, 1/2 up, down, and minus 1/2 down, up, and 0 down, down. So that's up, down, minus down, up. Not 1/2, sorry, 1 over square root 2. So it becomes a spin singlet, a combination of up, down, and down, up. And that's a spin singlet state. The same applies to these results, okay? So instead of writing those formulas in lines, in the future, we will just use these matrices to represent the so-called 1/2, 1/2 to 0 channel. So you should really think of channel as a projection operator. These operators takes, for example, 1/2 and 1/2, it has 4 states, 4 basis states. And these channels or projection operator takes 4 states and project into some number of states which is less than 4. So these channels always look like matrices which has less column than less row than column. For example, 4 column here project to 1 row, which means that I'm taking a 4-dimensional Hilbert space and project it into a 1-dimensional Hilbert space. Here, I'm taking a 4-dimensional Hilbert space, project into a 3-dimensional Hilbert space. So these matrices tells us how to recombine the bases in the previous larger Hilbert space and then project separately into each channel or each sector or whatever. So this is like a communication channel or fusion channel, yeah, of these particles. So the matrix element that appears in these matrices are very important, so important that people give it a name called the Clebsch-Gordon coefficient. If you read other textbooks, they will also introduce this concept. But this concept is simply the combination factors that you need to apply in order to combine the previous basis state in the larger tensor product Hilbert space down to the basis state in the reduced, irreducible representations into the separate irreducible representations. So this coefficient is just another big table that can tell you how to do these combinations, okay? This coefficient, don't worry about that. If you are using Mathematica, you can actually, there's a function called the Calabish-Gordon coefficient. Mathematica can directly tell you what are these coefficients. But anyway, you will not be examined by asking you to answer these coefficients. So you just need to understand that there's a concept. We need some coefficient to recombine our tensor product states into the irreducible representations, okay? Any questions? Yes, sorry.
Can you explain how we wrote down like the S1 and S2 and S3 matrices in the first, like in the 1/2, tensor 1/2?
Yes. Very good. Maybe we can go through that. So first of all, we need to write down SA1, SA2, and SA3. The way to write it down is follow the definition. SA1 corresponds to Pauli matrix X acting on the A particle and identity acting on the B particle, which is this Pauli, and this is what I wrote there. I hope this is understandable. And following the same principle, you write down SA2, which is a Y Pauli matrix acting on A particle and identity on B, and then SA3, which is these three guys. Okay? Then we write down the same thing for SB. It's very tedious, but it's the same thing. So for example, I just look at this SB1, which is sigma X acting on the B particle but identity on A. So you can see identity on A, sigma X on B. And then following the same rule, expand the first matrix and then duplicate the second matrix. So you can see I'm expanding the first matrix into a big 1 here, 1, 0, 0, 1. And then copy the second matrix, so it goes to here, 0, 1, 1, 0. This part is copied from here. This part is also copied from here. The other two off-diagonal blocks is 0 because these two elements are 0. So following the same principle, you can also write down SB1, SB2, SB3. Now, you just need to add SB1 with SA1. So SA1 is this 4x4 matrix. SB1 is this 4x4 matrix. If you add them together, let me write down the answer here. If you add them together, these two matrix element also becomes 1, and then these two matrix element also becomes 1. Okay, so that is S1 operator. That is S1 here. And then you can see that this is the result. This is the result. I just have an overall 1/2 factor, but other than that factor, if I factor out, it's 1, 1 in the first line, and then 1 here in the second line, 1, 1, second line, 1, 1. Okay? So you just need to follow all the definitions, tensor product the Pauli matrices with together, and then sum them as you need to sum them, and then everything will go through. And then you can do that for SY and SZ, which I call S2 and S3, and then you can further combine them to calculate S squared. S squared is just this guy's square plus this guy's square plus this guy's square. These are all matrix square. And then you can verify if you do that, in this representation, you will get that. The reason that we want to change a representation because these things are very complicated. You need to go through such a terrible calculation. But if you already know that spin 1/2 tensor spin 1/2 will fuse to 0 and 1, you can immediately write down all this. These are not written by of course, you can obtain this by diagonalization and by finding basis transformation following what we do. But if you already know that the answer must look like that, you can directly write down this answer because this answer simply corresponds to what S1, S2, and S3 should be represented if they were represented in the spin 0 and spin 1 basis. So that's what it brings you, that simplified the problem. And the basis transformation you need to do is actually called the Calabish-Gordon coefficient. So that's also, you don't need to diagonal. In principle, these coefficients are all computed by matrix diagonalization following what we have done. But people have done it so many times that they form a table. And then you can look up the table. And Mathematica also has a function which encodes all these coefficients. So you can simply look up these coefficients and understand how the projection works. Okay, I guess that's it for today. Thank you for your attention. Yeah.